All comet experts on Earth agree that Comet Atlas is behaving in a way they have never studied before. As this intercomet object hurtles towards a collision with Mars in October, it is developing an expanding green atmosphere stretching beyond Jupiter's diameter, its brightness increasing suddenly and unusually. Its tail defies solar physics and its dust scatters light in ways never previously measured. The closer it gets to the red planet, the more it looks designed rather than natural. But this is the truly strange thing no AI mentions. While amateur astronomers worldwide flood social media with experimental images of this cosmic anomaly, every major space telescope like Hubble, James Webb, Gemini has been mysteriously silent since August. Stay with me until the end of this late-night dive as we explore why Comet Atlas is acting so strangely, and most importantly, why officials are completely silent about the most significant astronomical event of the 21st century. A comet refuses to behave in mid-2025. An unwanted event has occurred. Comet Atlas suddenly brightened faster than model predictions as it approached about 2 astronomical units from the Sun. The question astronomers are struggling with is simple but worrying. To understand the seriousness of this anomaly, you need to understand what the predicted light curve means. In human terms, think of it as a cosmic weather forecast. But instead of predicting rain or shine, astronomers calculate the exact brightness of a comet as it approaches our star. These predictions are not random guesses, but based on tens of thousands of comet observations, complex models of how ice sublimates in the vacuum of space, and our understanding of how dust particles scatter sunlight over many weeks. Comet Atlas followed the scenario perfectly. Professional and amateur astronomers worldwide tracked its steady brightening as it moved in from the distant regions of the solar system. The data matched predictions. Brightness increased predictably as the comet heated up, releasing more gas and dust, forming the characteristic hazy atmosphere. Then, from 7 to 15 September, something changed. Observers reported data points soaring beyond the expected trend. In astronomical terms, Atlas jumped lanes, and the deviation was not subtle when plotted on a magnitude scale, the standard astronomers use to measure comet brightness. The light curve showed a clear departure from the predicted path. It was as if something suddenly hit the gas pedal on a car speeding along. But this is when the mystery deepens. The astronomy community is actively debating whether this brightening is a genuine comet outburst, or something more ordinary called the aperture effect. This is a technical term describing how telescopes of different sizes and observation methods can amplify measured brightness deviations. Imagine trying to measure the size of a campfire from afar. If you squint and look through a narrow tube, you might only see the brightest flames at the center and conclude the fire is small but intense. Open your eyes wide and suddenly you notice the full extent of glowing embers and flickering light spreading much further than you initially thought. Different telescopes with varying apertures and detection methods can experience similar differences when observing the comet's expanding hazy atmosphere. The best public data curves are found in the observation database. The comet, known to astronomers as C-223A3, these charts at a glance show Comet Atlas as a steep Leo curve suddenly in mid-September. The slope change is undeniable, even if the interpretation remains controversial, to gauge the scale of what we are witnessing. Consider the comet's speed as it rushes towards. Comet Atlas is moving at tens of kilometers per second, equivalent to about 210,000 km/h, fast enough to cross a 6 Earth in less than a minute, closest to the Sun. Called perihelion, the press reports it will reach about 68 kilometers per second. The timing of this cosmic encounter has been precisely calculated. Perihelion will occur at the end of October, specifically from 29 to 30th October, at a distance of about 1.36 to 1.4 astronomical units from the Sun. To visualize, that distance lies just within the orbit of Mars. Speaking of Mars, Atlas will fly close to the red planet on 3:10, approaching within about 0.19 astronomical units, an appointment in the sky. This has attracted the attention of mission planners and spacecraft operators currently orbiting Mars. The high-resolution scientific imaging experiment called HiRISE, along with the color and stereo surface imaging system called KSIS, and the high-resolution stereo camera named HRSC, are all planning to observe Atlas, the visitor to Mars. So what is really happening there? A simple explanation in Vietnamese is clear, but worrying. Either Atlas is releasing more gas and dust in ways that our models do not predict, or our instruments are detecting a very large Martian atmosphere like coma in a way that has fooled our calculations, or both phenomena are occurring simultaneously. These mysteries go far beyond academic curiosity. This is only the third confirmed interstellar object ever discovered in our solar system. Unlike typical comets, originating from the Kuiper belt or the Oort cloud and following predictable orbits around our Sun, Atlas comes from a completely different place. Its behavior will provide important insights about the composition and characteristics of objects from other star systems. However, it refuses to obey the rules that we have established through centuries of comet observation. The unusual brightness indicates our understanding of these visitors from interstellar space is still embarrassingly incomplete. Are we missing fundamental aspects of how these objects operate? Do comets from other star systems behave according to different principles than our local specimens? At this moment, it could not be more exciting as Atlas approaches its closest point to the Sun. Every telescope on Earth and in space is preparing to closely examine this visitor from the stars. What they discover in the coming weeks could revolutionize our understanding of what exists in the space between stars. But this unusual phenomenon is just the beginning of Atlas's strange behavior. The hazy atmosphere surrounding the comet's nucleus expands to an absurd size. Developing faster than physical limits allow, Atlas, the mysterious phenomenon from interstellar space, Part 2. Expanding faster than physical limits. The hazy cloud around Atlas is not only unusual in its rapid brightening, but is also expanding at a rate that challenges our fundamental understanding of how comets work. To understand why this matters, you first need to understand what astronomers mean when they refer to a comet's coma. Think of the coma as the comet's atmosphere, but unlike the neat atmospheric shell, bound by Earth's gravity, a comet's coma is a chaotic, ever-changing mixture of gas, dust, and plasma extending hundreds of thousands of kilometers into space. When ice on the comet's surface heats up and sublimates, directly from solid to gas, it carries dust particles with it, creating a giant envelope that can be larger than planets. On 6/8/2025, the James Webb Space Telescope turned its infrared gaze towards Comet Atlas and discovered something extraordinary. The comet's coma shows an unusually high concentration of carbon dioxide compared to water vapor. This ratio is extremely unusual for comets, suggesting that Atlas formed in a very cold region of its original star system, or has undergone a very different chemical evolution compared to the comets we know. At the comet, this dominance of carbon dioxide is important. Unlike water ice, which requires significant solar heat to sublimate, carbon dioxide begins to evaporate at greater distances from the sun. This means that Atlas starts becoming active much earlier in its approach, compared to typical comets. Essentially, the comet woke up very early and began its spectacular display, while still in the distant reaches of our solar system. Further analyses using near-infrared spectroscopy revealed a carbon dioxide gas layer, expanding with the envelope stretching hundreds of thousands of kilometers into space. Some estimates suggest the total volume of this envelope is about 700,000 km, roughly half the diameter of the Sun. However, it is important to note that this figure is only an estimate reported, not a scientific consensus, due to varying observational methods, and analytical techniques can provide various measurements from the 21/7 imaging by the Hubble Space Telescope, have provided another piece to this puzzling picture. Observations show a compact nucleus completely obscured by a bright dust cocoon through brightness modeling techniques. Astronomers have set an upper limit for the nucleus radius at about 2.8 kilometers. This direct discovery contradicts claims about a gigantic size that have spread widely on social media and some news channels. Additional confirmation comes from the Vera Rubin Observatory Legacy Survey of Space and Time, which took images in June and provided data, tracking the nucleus within a few kilometers. Some reports cite diameters from 4 to 5.6 kilometers, but scientists emphasize the inherent uncertainty in these measurements. The actual size remains within a range rather than a precise value. To understand the nature of the extended coma of Comet Atlas, we need to grasp the concept of dusty plasma. Simply put, this refers to a mixture of neutral dust particles and gas molecules, some of which have been ionized by solar radiation. This ionized matter does not behave like ordinary matter but self-organizes into complex structures, forming filaments and networks that may appear to flicker and shift according to seemingly organic patterns when observers report seeing living patterns in the coma of Comet Atlas. They are witnessing the physics of plasma self-organization. Magnetic fields running through the ionized gas layer create invisible pathways along which charged particles move, forming complex structures visible in high-resolution images. These patterns arise from the same principles, governing the dancing auroras in polar skies or the giant plasma loops erupting from the solar surface. But what makes Comet Atlas puzzling is the combination of a giant halo containing abundant carbon dioxide rapidly expanding, representing an unprecedented combination for an interstellar visitor. The first interstellar object, Oumuamua, showed no clear cometary activity. The second, 2I Borisov, behaved like a typical comet. From our own solar system, Comet Atlas lies somewhere between these two extremes, exhibiting clear cometary features, while displaying chemical and physical properties that do not fully match our expectations. The dominance of carbon dioxide, combined with the rapid expansion of the coma and unusual brightness evolution, suggests we are dealing with an object challenging our current classifications. The rapid growth rate of the coma itself raises fundamental questions based on the solar heating Atlas receives at its current distance and the known sublimation rates of various ices. The coma should expand at a predictable rate. However, observations show the coma is growing faster than standard models predict, as if an additional energy source is driving the sublimation process. Could the comet be undergoing internal self-heating due to radioactive decay? Unlikely, given its small size. Could it spin fast enough to generate extra pressure, causing surface cracking and exposing fresh ice? Possibly, but unproven, or perhaps its unique composition includes volatile materials that our Earth-based experience does not teach us how to predict. This plasma factor adds another layer of complexity when the solar wind, a stream of charged particles, continuously flowing from our star, encounters the comet's extended gas layer, creating a shock wave similar to the wake of a boat moving through water. This interaction may accelerate the gas expansion and produce nearly lifelike filamentary structures. However, even accounting for these plasma effects, the growth rate seems too fast, like Comet Atlas, behaving according to a different set of rules compared to the comets we have studied for centuries. Carbon dioxide chemistry provides part of the explanation but not the whole picture. As we observe this interstellar visitor, continuing to approach the inner solar system, each new observation raises more questions than answers. The expanding envelope continues to develop, fed by sublimating ice chunks that probably should not be so active at the comet's current distance from the Sun. But expansion is not the only mysterious aspect of its behavior. Atlas comet as astronomers continue observing throughout the summer months. They noticed something even more astonishing than the comet's shell color beginning to change, emitting a strange blue light, making any science fiction filmmaker proud. The blue light over the clear Namibian sky, dark during the nights from 7th to 17th of September. Amateur astronomers recorded something remarkable. Their photos showed the comet glowing with an unmistakable blue hue, a color so vivid it seemed almost artificial against the star-filled backdrop of space. Blue is not unprecedented in astronomy. This phenomenon occurs when diatomic carbon molecules, consisting of two carbon atoms bonded together, glow under the influence of solar ultraviolet rays. These molecules absorb photons of high energy from the Sun and emit energy as visible light at a wavelength of about 518 nanometers, which our eyes perceive as blue. Under normal conditions, this process happens in a predictable sequence. When a comet approaches the Sun, the temperature rises, breaking down complex carbon-containing molecules in the nucleus, producing diatomic carbon that emits the characteristic blue light. The intensity of this fluorescence correlates directly with the amount of solar radiation the comet receives and the abundance of carbon-containing materials in its composition. But the blue light of Atlas poses a puzzle that does not fit this standard model. Initial spectral analysis showed this comet is unusually rich in carbon dioxide, while only showing limited signs of classic carbon chemistry, which usually produces the blue fluorescence. This combination should have resulted in much weaker or delayed blue light compared to what observers actually witnessed. The timing and intensity of Atlas Comet's blue light appeared earlier and stronger than expected, based on its distance from the Sun or its unusual chemical composition. Scientists describe this discrepancy as surprising and acknowledge that the phenomenon is still under active investigation. The comet seems to be turning blue earlier and more intensely than its carbon dioxide chemical composition would predict. To understand why this is important, consider the delicate balance of chemical reactions occurring in the comet's coma as solar radiation heats the nucleus. Different volatile materials sublimate at different temperatures and distances from the Sun. Water ice requires significant heating. Carbon dioxide turns to gas much earlier, and complex carbon molecules break down into simpler forms at various stages throughout the process. The blue light indicates carbon-containing molecules are breaking down and being excited by solar radiation. But the timing suggests this breakdown is happening earlier or more efficiently than predicted by models, as if the Atlas comet contains carbon chemistry we have never encountered before, or solar heat is affecting its materials in unexpected ways. A plausible explanation involves chemical changes occurring as the comet continues to approach the Sun and temperatures rise, significantly altering the chemical composition of the comet's gaseous envelope. Molecules stable at greater distances from the Sun begin to decompose, producing new chemicals that may fluoresce in different ways. The green emission could represent this chemical transition occurring faster or more extensively than usual. It is important to understand that the green color does not mean the comet's nucleus itself is green. The solid core at the center of Atlas Comet may still be a dark mixture of ice and dust, possibly red or brown like many comets and asteroids. The green light comes entirely from the gaseous envelope surrounding the nucleus, extending thousands of kilometers into space. This distinction becomes important when considering the relationship between blue fluorescence and the previously discussed brightness anomaly. If the coma becomes denser with gas and dust, and if specific molecules like diatomic carbon become more abundant, then blue emission will naturally intensify. These two phenomena may be related aspects of the same underlying process. Think of it like neon signs lighting up when electricity passes through them. The blue light of Atlas Comet may be telling us that the internal chemistry of the comet is accelerating faster, expected to be powered by solar energy with a stronger impact than our models predicted. However, interpreting visual evidence must be done cautiously. Digital cameras and image processing techniques can enhance colors far beyond what the human eye sees directly. The beautiful green photo spreading online may be more vivid than what you see through a telescope. However, the spectral line at 518 nanometers represents the actual physics, confirming that carbon in molecular form is indeed fluorescing in the comet's shell. This blue-green light also provides clues about the comet's rotation and internal structure. If Comet Atlas rotates quickly, different regions on its surface will successively be exposed to heat from the Sun, potentially causing changes in the intensity and distribution of the blue-green fluorescence. Some observers have reported significant changes in brightness and extent of the blue-green light over hours or days, indicating the comet's nucleus may indeed be rotating. The psychological impact of the blue-green light cannot be underestimated. Throughout human history, unusual celestial phenomena have inspired both awe and anxiety. A comet appearing green, especially one originating from interplanetary space, naturally evokes thoughts of the strange and extraterrestrial. Science fiction has shaped us to associate green light with strange technology or alien origins. However, astronomy has taught us that nature often produces phenomena even more spectacular and strange than anything science fiction writers can imagine. The blue light of Comet Atlas, though unusual in timing and intensity, represents chemical processes actually occurring under the harsh conditions of space. A comet is essentially a natural laboratory where materials from another star system are heated and transformed by solar radiation. As Comet Atlas continues its journey towards perihelion, the blue light may become even more intense. Increasing solar radiation will break down more carbon-containing molecules, potentially creating even more spectacular visual displays. Amateur astronomers worldwide continue to record these changes, contributing valuable observations and understanding scientific knowledge about this interstellar visitor. The green fluorescence is only one aspect of Comet Atlas's unusual appearance, but perhaps the most visually striking. Combined with the rapid expansion of the coma and unusual brightening, the blue light contributes to an overall impression of a comet unlike anything we have seen before. Yet even the strange blue light pales in comparison to a geometric oddity that astronomers are baffled by. While conspiracy theorists are working overtime, something about the way Comet Atlas's tail is oriented seems to defy fundamental physical laws about how comets should behave in the solar wind. Part 4. The Reverse Tail and Strange Geometry. In standard textbook images of comets, tails point away from the sun, formed by continuous solar radiation pressure and charged particles in the solar wind flowing outward. This basic principle has held true for every comet observed by humans, from ancient comet appearances to spectacular displays in recent decades, until Atlas decided to break the rules. To understand why this matters, you need to grasp the physics behind comet tail formation. Typically, when a comet approaches the sun, solar radiation pressure pushes dust particles away from the nucleus, creating a curved dust tail following the comet's orbit. Meanwhile, the solar wind, a stream of charged particles continuously flowing from our star at hundreds of kilometers per second, ionizes gas molecules in the comet's head and carries them into a straight ion tail. Pointing directly away from the sun, these two tails, the curved dust tail and the straight ion tail, create the classic image we associate with bright comets. The physics is simple: particles and ionized gas follow the path of least resistance when pushed by solar forces. The sun is the dominant influence and everything flows away from it. But initial observations of Comet Atlas revealed something that shouldn't exist: a stream of material pointing towards the sun, what astronomers call a reverse tail. Instead of matter flowing away from the sun, There seems to be a sharp dust and gas tail pointing directly towards our star, as if the comet somehow challenges the solar wind and radiation pressure before you start wondering about gravitational thrust or alien propulsion systems. It is important to understand that the reverse tail, although rare and impressive in appearance, has natural explanations. They are the result of a combination of observational geometry and the three-dimensional structure of dust and gas surrounding the comet's nucleus. Imagine, you are looking at a thin dust sheet. Particles seen obliquely from Earth's perspective, if this tail extends both towards and away from the sun. But we are viewing it from an angle where the sunward part seems projected onto the sky. It can create the illusion of matter flowing towards the sun. The reverse tail does not actually defy physics. It is a trick of perspective caused by our specific position. The geometry becomes more complex when considering the orbital characteristics of Comet by Atlas. This comet follows an almost retrograde orbit, inclined about 5 degrees relative to the ecliptic plane, the flat disk around which most planets orbit the Sun. This unusual orientation maximizes the potential for strange perspective effects when observed from Earth. Later observations, including stunning images taken by the Gemini telescope on 27/8, showed the development of a sunward tail, more typical, pointing away from the sun as expected. But the earlier sunward smoke column attracted attention and sparked speculation about the comet's unusual nature. Polarimetric measurements, a technique analyzing how light waves are oriented when scattered by dust particles, revealed further complexities in Atlas's tail structure. Polarimetric measurements indicate structured dust and organized plasma distribution that do not match simple models, commonly used to describe comet tails. These polarimetric results are consistent with the complex coma structure, meaning the gas and dust surrounding Atlas's nucleus are arranged in more complex ways than the relatively simple spherical or elongated distributions seen around most comets. Think of it as the difference between a smooth balloon and a complexly folded origami sculpture. Both are made from the same type of paper, but have very different structural complexities. The reverse tail phenomenon, combined with the high speed and unusual orbital inclination of Atlas, has created a visual spectacle that naturally arouses suspicion among casual observers and even some experienced astronomers. The comet seems to defy the fundamental forces governing how objects behave in our solar system. This apparent challenge to natural laws only increases the psychological appeal of strange explanations when faced with phenomena that seem to violate basic physical laws. The human mind naturally turns to more dramatic interpretations. If a comet appears to push back against the solar wind, perhaps it is not a comet, but something with its own propulsion system. More mundane is often seen in astronomy, but no less fascinating than strange hypotheses. The reverse tail is the result of the same geometric principles that create optical illusions on Earth, like a straight road that can appear curved when viewed from certain angles, or distant mountains that can seem to float on the horizon under specific atmospheric conditions. The reverse tail of Atlas represents a real phenomenon, arising from natural causes. The nearly flat and coplanar orbit that this comet follows plays an important role. in maximizing these perspective effects for observers on Earth. As the comet moves through three-dimensional space, different parts of its extended dust and gas envelope become visible or hidden depending on our viewing angle. What we see as a sunward tail may actually be matter flowing in many different directions, with only a few components visible from our specific viewpoint. Understanding the reverse tail phenomenon requires thinking in 3 dimensions while interpreting 2-dimensional images. It's like watching shadows on a wall and trying to deduce the shape and orientation of the objects casting those shadows. Those shadows provide information, but to interpret them accurately requires understanding the geometry involved, as Atlas continues to approach perihelion. Its reverse tail may develop different viewing angles that will reveal or conceal the various components of the extended atmosphere of the comet star, likely to produce new geometric surprises challenging to astronomers. Lies in distinguishing between actual physical anomalies and apparent oddities caused by viewing angles of the comet star by Atlas. Is a perfect example of how an object that appears alien actually follows completely natural physical principles. The unusual appearance of this comet star results from a combination of real chemical and physical characteristics, enhanced by observational geometry amplifying the striking oddities of geometry and perspective effects. Pales in comparison to an aspect of the Atlas comet which genuine scientists use words like unprecedented and anomalous. The way this comet star polarizes light shows features that do not match any object ever studied from our solar system, or beyond the fifth part of a swarm in the autumn sky of 2025, has turned Earth's night sky into something resembling a cosmic traffic jam, with many bright comet stars sweeping through the inner solar system, simultaneously creating a spectacle in the sky unseen for 10 centuries. At the center of this swarm, 3 Atlas comets cross like visitors from another star system surrounded by a supporting ensemble of comet stars originating much closer to Earth. Their appearance timing creates a remarkable convergence of cosmic events. Comet C on 2.0214. The orbit reaches perihelion on 12/9, and will approach Earth closest around 2110 at a distance of 0.215 astronomical units. That is about 23,000 miles, close enough to potentially be seen with the naked eye under a dark sky. 410. Bon P on stereo. A periodic comet returning to the inner solar system every 7.5 years. Reached perihelion on 27/9 at approximately 0.52 astronomical units from the Sun. This comet was discovered by the Solar and Heliospheric Observatory spacecraft, adding another bright point to the autumn sky, perhaps the most spectacular of which is Comet Leonard, predicted to reach magnitude 4 at closest approach. This comet will reach perihelion on 8/11 at about 0.53 astronomical units from the Sun, potentially making it visible to the naked eye, even from moderately light-polluted locations, to understand that many comets can appear in our sky, simultaneously without any physical connection. Imagine cars on different highways heading towards a city. From many different directions, comets follow separate orbits that coincidentally bring them through the inner solar system, at the same general time, creating the illusion of coordination without any real relationship between the objects. The result of visual clustering comes from the combination of orbital mechanics and observational bias making comets visible to observers on Earth only when they are close enough to the Sun to develop significant heads and tails. and are positioned in parts of the sky dark enough to observe the apparent coincidence of many bright comets, reflecting statistical data on comet orbits, rather than any physical connection between the objects, but the comet swarm. In autumn only represents a portion of the celestial activity that has characterized recent weeks in mid-September, has brought an additional wave of notable events in the form of many near-approaching asteroids, creating a news cycle flooded with headlines about near-Earth objects and potential threats. The most notable event was the close flyby of asteroid 2022 FA22 on 18/9, although completely safe. As the asteroid passed at a distance of several million kilometers, this flyby generated significant media coverage and discussion. On social networks, the combination of the asteroid's name naturally evoked thoughts about 2025. And the timing coinciding with comet activity created a heightened awareness atmosphere about moving objects in the neighborhood. Earth. Many smaller asteroids also pass nearby but safely in the same period, each time creating its own short news cycle. The concentration of these events in a short time contributed to creating the feeling that September 2025 is an unusual phase, with many near-Earth objects approaching in reality less dramatic. Considering more than what this concentration might suggest, asteroids frequently fly relatively close to Earth, with most approaches unnoticed by the public. The clear wave of asteroid activity in mid-September reflects improved detection capabilities of modern survey telescopes, rather than any real increase in the number of objects approaching our planet. However, the psychological impact of many comet and asteroid events occurring within a short period cannot be ignored by the human brain, which inherently seeks patterns. And when faced with multiple related events occurring consecutively, it tends to infer connections even when none exist. This pattern-seeking tendency becomes especially pronounced when we face astronomical phenomena throughout history. Unusual configurations of comets, planets, and other astronomical events have been interpreted as omens, messages, or signs of important events about to happen on Earth. The abundant appearance of comets and asteroid activity today naturally triggers similar psychological reactions in those inclined to more unusual interpretations. This timing raises interesting questions. If an advanced civilization wanted to send reconnaissance probes to survey our solar system, would they coordinate their appearance to coincide with natural comet activity? It is logical that disguising artificial objects among astronomical phenomena would provide the perfect cover for secret observation. Such a strategy would be highly effective. Natural comet swarms appear periodically when gravitational disturbances beyond the solar system send many objects into sun-approaching orbits. Within a relatively short period, any artificial object arriving during such times would blend into the crowd, difficult to distinguish from natural phenomena unless analyzed in detail. Speculation becomes even more interesting when you consider the characteristics that make some orbits particularly attractive for reconnaissance purposes. An orbit passing close to many planets like the swarm of Lullaby would provide opportunities to study different worlds in a single mission. Comets will pass relatively close to Mars, allowing detailed observation of that planet before continuing inward toward the Sun. From a purely strategic perspective, its current period represents an ideal time for secret monitoring of natural comet activity, providing cover in the abundance of bright objects in the sky. ensuring that any individual anomalies can be overlooked and public attention has focused on astronomical events, making unusual phenomena seem less noticeable. Of course, the more common explanation remains more likely gravitational interactions beyond the solar system occasionally send many comets on inward trajectories in overlapping timeframes, creating natural swarms like the one we are witnessing. The detection of asteroids shows frequent discovery of objects that have always been there, now becoming visible thanks to improved survey capabilities. But as Atlas continues to approach the inner solar system, distinguished from other celestial bodies by its interstellar origin and unusual characteristics, we must ask whether we are witnessing a natural coincidence or something deliberately arranged. The question becomes more urgent when we consider a final, hard-to-explain piece of data: how Atlas polarizes light when reflecting sunlight towards Earth, showing such unusual features that some scientists struggle to find natural explanations to fully explain what they are observing. Part 6. Natural or artificial? The question haunting astronomy in 2025 is not whether Atlas is unusual, but whether the strange features of the comet indicate natural phenomena we do not yet understand, or something challenging our assumptions about what can exist in interstellar space. To address this properly, we need to consider precedents set by two previous interstellar objects that entered our solar system one eye. Oumuamua, discovered in October 2017, defied all expectations by showing no clear cometary activity, despite following a hyperbolic orbit clearly indicating its origin outside the solar system. Instead of developing the characteristic gas trail and tail of a comet, Oumuamua remained motionless, resembling a rotating asteroid rather than a typical icy comet. Even more puzzling was that Oumuamua exhibited a small but measurable acceleration that could not be explained by gravity alone. An anomaly. This acceleration sparked intense scientific debate and inevitably speculation about an artificial origin. If the object were an abandoned spacecraft with residual outgassing or even some form of strange propulsion, then that acceleration could be reasonable. However, for a natural object, that acceleration proved difficult to explain satisfactorily. 2I Borisov, discovered on 8/19/2000, created a stark contrast with its predecessor, the interstellar visitor. This second comet behaved exactly like a textbook comet, developing a significant gas envelope and tail. As it approached the Sun, spectral analyses revealed a composition similar to comets from our solar system, indicating that comet formation processes may be relatively common, regardless of which star in the system acts as the birthplace. Now the Atlas comet lies somewhere between these two extremes, clearly showing cometary features but with chemical and physical properties that do not fully match our expectations for local or interstellar comets, including carbon dioxide content, unusual polarization properties, and rapid expansion of the shell create a combination of challenging factors. Current classifications have issues. The nucleus size deserves careful attention, as it directly affects how we interpret other comet characteristics. Observations from the Hubble Space Telescope have set an upper limit for the nucleus radius at about 2.8 kilometers, corresponding to a diameter under 5.6 km. Many ground surveys show a size within a few kilometers. Certainly not the 50-kilometer monster some initial speculations suggested. This size constraint is crucial because it limits the amount of material available to create a large cometary coma and tail. A small nucleus simply cannot contain enough volatile material to sustain the level of activity that Comet Atlas is displaying. Unless that activity is unusually efficient, or the composition significantly different from typical comets, the appeal of artificial explanations becomes understandable when faced with these clear contradictions. If Atlas does not behave like a natural comet, then perhaps it is not a comet, logically suggesting an artificial object, which could easily explain the unusual combination of small size, high activity, and strange composition. However, science generally favors natural explanations until evidence decisively disproves them. This principle, known as Occam's razor, states that the simplest explanation accounting for all observed phenomena is most likely correct before excluding an artificial origin. Astronomers reconsider every natural mechanism that might explain that unusual behavior. A few natural processes could potentially explain the oddities of Comet Atlas, a volatile composition significantly different from solar system comets could explain the early onset of activity and unusual chemistry. Surface texture and structure could affect the nucleus's efficiency in releasing gas and dust when heated by solar radiation. Rapid rotation could generate centrifugal force enhancing material ejection. Internal fracturing or fragmentation could expose new volatile rich material to solar heat. Polarization data mentioned earlier provides particularly powerful diagnostic capability when light reflected from dust particles in the comet's shell. The direction of light waves carries information about the size, shape, and composition of those particles. By measuring how reflected light is polarized, astronomers can infer characteristics of the scattering material not obvious from brightness measurements alone. Comet Atlas exhibits polarization with features unmatched by any comet, asteroid, or other object in the solar system studied before. Extreme negative polarization values at small phase angles, with a minimum of about 2.7% at around 7 degrees, are unprecedented measurements, challenging current understanding of how dust particles scatter light. These polarization anomalies may indicate the unusual dust particle properties caused by irradiation during the long journey of the comet through interstellar space, strange components not found in objects of the solar system, or even artificial materials with optical properties different from what nature usually produces. Comments from reliable researchers, including views shared on academic blogs and preprint servers acknowledging these oddities, while maintaining scientific caution about their interpretation. The polarization data is real and represents a significant puzzle, but extraordinary claims require extraordinary evidence. The artificial hypothesis faces several significant challenges. No confirmed radio signals have been detected from the Atlas object despite multiple searches by observatories. The comet shows no evidence of course correction or any other maneuver that might indicate active control. Its orbit, although unusual, still fits gravitational dynamics and does not require invoking even stranger systems. If Atlas is artificial, It would represent technology operating on a scale and time frame far beyond human capability. The journey from the original star system to our solar system would take thousands, even tens of thousands of years, assuming the object moves at a speed comparable to our fastest spacecraft. Any civilization capable of such long-duration missions would likely possess technological capabilities far beyond our current understanding. The natural hypothesis requires expanding our knowledge of stellar physics and interstellar chemistry, but does not require the existence of advanced extraterrestrial technology, although the Atlas object certainly pushes the limits of what we consider possible for natural objects. It does not completely cross the boundary to demand artificial explanations. As observations continue and more data is obtained, the scientific community will gradually arrive at the most reasonable explanation for the unusual characteristics of the Atlas object. This process may take months or years, but ultimately the weight of evidence will lean towards a strange natural phenomenon, or something more extraordinary. This identification has significance far beyond academia and curiosity. If the Atlas object proves to be artificial, it would represent the first confirmed contact with technology from another star system, fundamentally changing humanity's understanding of our place in the galaxy. But before we reach such revolutionary conclusions, we need to consider whether the Atlas object could be part of something larger. What if this comet is not traveling alone, but is merely a fragment of a massive debris field scattered throughout interstellar space, caused by some ancient catastrophe? Part 7. Hypothesis of debris fields. Sometimes the most extraordinary explanations arise from the most catastrophic events. Consider the possibility that Atlas, along with other unusual objects appearing in our sky, represent fragments from a cosmic disaster that occurred thousands or millions of years ago in a distant star system. The implications of this hypothesis stretch our imagination, while remaining within the limits of known physics. Debris fields can be ejected from star systems through several mechanisms, each mechanism capable of dispersing material across interstellar space at speeds sufficient to eventually reach neighboring systems. The planet formation stage is one of the most chaotic phases in the evolution of any star system, with giant bodies colliding, fragmenting and ejecting countless smaller objects into space. The early solar system underwent similar devastation with the formation of our moon, possibly the result of a Mars-sized object colliding with the early Earth. Close encounters between stars also provide a mechanism to eject debris. When two star systems pass close by, gravitational interactions can push objects out of their original orbits, sending them on trajectories between stars. Computer simulations show such encounters occur frequently throughout galactic history, creating a steady flow of interstellar wanderers. Furthermore, significantly, catastrophic disintegration of planets or large moons can scatter debris over vast distances, whether due to tidal forces in close encounters of stars or internal processes, such as the greenhouse effect spiraling out of control, or even technological disasters on a planetary scale. Such events would create expanding layers of material, moving at high speed through interstellar space. The carbon dioxide component of the biolayer provides potential clues about its origin. This chemical component indicates formation under extremely cold conditions, possibly in the outer regions of another star system, where carbon dioxide ice can remain stable over geological timescales. Such conditions may exist in the disk of material in a star system that has undergone violent disruption with material ejected before it could undergo thermal processing, which typically occurs during normal planet formation. The red spectral slope observed in some analyses of Atlas also suggests an unusual history. This color may result from cosmic ray radiation during a journey long across interstellar space, or it may reflect an original origin from material components formed under conditions different from objects in our solar system. The red recalls objects in the outer system of the Sun that have been altered by millions of years of radiation exposure. The polarization anomalies discussed in previous sections may support the hypothesis of a debris field if the Atlas article includes materials that was processed differently during formation or experienced unique conditions during its interstellar journey. Then, the dust grains forming it may have optical properties unlike anything in our local environment. Unusual dust structures may arise from shock processing in a catastrophic eruption event or from gradual alteration by interstellar radiation over millions of years. The appearance of objects clustered in the sky does not necessarily prove they share a common origin. However, the clear coincidence of many unusual objects appearing within the same time frame may be due to observational bias. Combined with improved detection capabilities, we are simply better at finding and tracking faint objects and transient phenomena beyond. The solar maximum conditions in 2025 may contribute to increased interest in cometary phenomena during periods of high solar activity. The interaction between solar wind and cometary atmospheres becomes more pronounced, potentially making boundary objects more visible and noticeable, compared to when the Sun is at minimum. However, if the Atlas is part of a larger debris field, we can expect to see additional interstellar objects in the coming years. Space heritage surveys and the timing of the Vera Rubin Observatory will significantly enhance our ability to detect faint, fast-moving objects, potentially revealing a population of interstellar visitors that have passed through our system unnoticed. The debris field scenario becomes more credible when you consider how such material would spread out over time. Imagine debris ejected from a catastrophic event like confetti thrown from a moving vehicle. Initially, the material may move in a relatively tight group, but over thousands or millions of years, gravitational interactions with stars and interstellar matter will gradually disperse the debris throughout space, increasingly widely. From our perspective, detecting debris from such an ancient catastrophe would be like trying to identify individual pieces of a fireworks explosion from thousands of miles away after the initial blast has occurred. Debris would arrive at different times and from slightly different directions, making recognizing their common origin difficult. Without detailed compositional and dynamical analysis, what evidence would support the debris field hypothesis? Shared compositional signatures among multiple interstellar objects would provide strong support, especially if those signatures differ significantly from solar system material. Similar dynamical properties such as comparable velocities and orbits, traceable to a common origin point, would further strengthen the argument. Advanced computer simulations could help test this hypothesis by modeling how debris from different catastrophic event types would disperse over time. If simulations predict arrival patterns and compositional distributions matching current observations, the debris field explanation would become more credible. The timescales involved in such scenarios are almost incomprehensible from a human perspective. If Alas originated from an event creating debris 15 years ago in a star system 55 light-years away, the comet would have traveled through interstellar space before humans developed agriculture. The disaster that created it could have occurred when our ancestors were still hunter-gatherers, completely unaware that cosmic violence was scattering debris. It would eventually reach their distant descendants from a broader perspective. The debris field hypothesis proposes a common point between strange natural phenomena and artificial origins, requiring no violation of known physics, no need for advanced alien technology, and no conspiracy theories about secret government knowledge. Instead, it simply asks us to consider that the galaxy may be more violent and chaotic than the current relative stability of the solar system. We suggest implications extending beyond the star map if interstellar debris fields are common. They could provide natural laboratories to study planet formation in other star systems, each fragment carrying information about the conditions and materials that existed in the original disaster, offering insights into the evolution of stars and planets that we could not obtain otherwise. Part 8. The Detective Theory. In 1960, mathematician and physicist Ronald Bracewell proposed a concept that still haunts the search for extraterrestrial intelligence. Instead of broadcasting radio signals across the distances between stars, Bracewell suggested that advanced civilizations could send autonomous probes to neighboring star systems. These probes would be much more efficient than radio waves in gathering detailed information about distant worlds and their inhabitants. The logic behind Bracewell probes is very convincing from a technical perspective. Radio signals weaken with distance according to the inverse square law, making communication between stars increasingly difficult over galactic distances. However, a physical probe can travel to a target system and conduct detailed surveys using sensors and instruments that cannot be deployed from light-years away, based on the concept of mathematician John von Neumann, who previously described self-replicating machines capable of building copies of themselves using local materials. Combined with Bracewell's probe idea, von Neumann probes could theoretically spread throughout the galaxy, with each probe creating additional copies upon reaching suitable star systems over millions of years. Such a program could cover the entire galaxy with a network of surveillance. The detective theory applied to Oumuamua requires us to consider whether this visitor to our star system might represent exactly such a reconnaissance mission, rather than revealing its artificial nature through obvious technological signs. An intelligent probe could disguise itself as a natural comet while conducting detailed observations of the solar system and its inhabitants. From this perspective, Oumuamua could represent our first glimpse of an active galactic civilization. But whether we are witnessing a natural phenomenon or something extraordinary, the implications are immense. Either the universe is far more violent and chaotic than the current stability of the solar system we observe, or we are seeing evidence of intelligence operating on a scale far beyond human capability. This stealth strategy would be brilliant. A natural comet provides the perfect camouflage for interstellar visitors. Following a predictable orbit creates a mechanism allowing a probe to survey multiple worlds. In one, pass through the solar system. Inside Oumuamua's orbit, it would pass Mars, offering a chance to study the atmosphere and surface of that planet before continuing inward to observe Earth and Venus up close. The timing could have strategic significance if the probe is designed to assess technological civilizations, arriving during solar maximum activity, as now, would provide an opportunity to observe our technology reacting to space weather events. The probe could monitor satellite communications, power grids, and other infrastructure to find vulnerabilities, potentially relevant for future interactions. Unusual brightness behavior could serve purposes beyond natural outgassing. If Oumuamua is equipped with sensors and communication devices, its variations can be controlled in its apparent brightness, which may represent data transmission or system checks on the rapid expansion of its atmosphere, possibly resulting from the deliberate deployment of sensor panels or antennas, communication disguised as natural phenomena. Abundant carbon dioxide could be an intentional choice, rather than random. In the process of forming carbon dioxide, providing an effective means to generate gas for altitude control and orbit adjustment, while maintaining the appearance of natural comet activity. A probe using carbon dioxide as camouflage can make minor adjustments, while still appearing to follow a purely gravitational orbit. The anti-tail shape may also serve two purposes. Although explainable through natural viewing angle effects, such a configuration would maximize the efficiency of the panel. If the probe is equipped with a power generation system, an artificial object could self-orient to optimize energy collection while creating visual phenomena, enhancing its comet-like appearance. The characteristic extreme polarization perhaps represents the most intriguing aspect of the probe hypothesis. Natural dust has never produced polarization signals like those observed from Oumuamua. However, artificial materials designed for specific optics or electronic functions could precisely exhibit these unusual scattering properties. Consider the material science requirements for a probe. Interstellar probes would need protection from cosmic ray bombardment, interstellar dust impacts, and extreme temperatures throughout the journey between star systems. Advanced composites or exotic coatings designed for these purposes could have optical properties unlike anything found in nature. The small nucleus size of the probe supports the reconnaissance hypothesis. An artificial object does not need to be large to carry advanced sensors and communication devices. Modern miniaturization technology has enabled extremely powerful devices, smaller than traditional satellites. Technology from an advanced civilization could compress even more functions into a scale of a few kilometers, consistent with Oumuamua's observed characteristics. However, the reconnaissance theory faces significant observational challenges. Despite extensive monitoring by radio waves and telescopes worldwide, no artificial signal has been confirmed from Oumuamua. The probe shows no evidence of course correction or maneuvers indicating active control of its orbit. Although unusual, it remains consistent with natural gravitational dynamics throughout the solar system. The technology required for successful interstellar reconnaissance would be formidable. The probe would need to survive thousands of years in the radiation-rich environment of interstellar space, maintain operational systems throughout the journey, and carry out complex mission objectives upon arrival. These technical challenges far exceed anything in human experience. Furthermore, if such probes exist, their creators likely possess technology far beyond interstellar reconnaissance missions. They may have detected radio waves and other technological signatures from their own systems. The need for close-range reconnaissance becomes less clear when dealing with such advanced capabilities. The reconnaissance hypothesis also raises questions about the motive and timing. Why would an advanced civilization choose a particular moment in history of humanity to send reconnaissance probes? Our technological signatures have been detectable for less than a century, a brief moment on a cosmic scale. The coincidence of the probe's arrival during humanity's technological adolescence seems very convenient. However, the combination of Oumuamua's unusual features and its coincidental timing creates a compelling story. If we were designing an interstellar reconnaissance mission, many observed characteristics would be entirely reasonable from a technical standpoint. The probe could be collecting data on the atmosphere, magnetic field, and technological infrastructure of our planet, while appearing to conduct purely natural observations. A purely natural phenomenon. Its close approach offers an opportunity to study many worlds, maximizing the enormous investment in interstellar travel. The most interesting thing, if Oumuamua is a scout ship from an advanced civilization, it may not operate alone. The clear concentration of unusual objects in our sky could represent a coordinated scouting effort with multiple probes conducting observations simultaneously from different favorable points. These raise perhaps the deepest question of all. If the galaxy contains civilizations advanced enough to launch interstellar scouting missions, at our star system we have never encountered clear evidence of their existence before. The answer may lie in one of the most famous puzzles of science. Part 9. The Fermi Paradox. Encountered the sky in 1950 during a casual lunch at Los Alamos National Laboratory. Physicist Enrico Fermi posed a question that has haunted science ever since. Where is everybody? The question simply highlighted a profound contradiction between the apparent possibility of extraterrestrial life and the complete lack of evidence for that existence. The mathematics behind Fermi's question was formalized through the Drake equation, developed by astronomer Frank Drake in 1961. This equation attempts to estimate the number of civilizations capable of communication in our galaxy by multiplying factors such as the rate of star formation, the proportion of stars with planets, the number of habitable worlds per planetary system, and the probability of life developing intelligence and technology. Even the most conservative estimates using the Drake equation suggest our galaxy should contain thousands or millions of technological civilizations with 400 billion stars in the Milky Way and billions of years available for life to evolve. The absence of obvious alien visitors seems statistically impossible. The discrepancy between expectation and observation defines the Fermi paradox. Interstellar objects like Oumuamua provide new data for some terms in the Drake equation. the discovery of thousands of exoplanets has confirmed that planet formation is common, addressing the factor representing the proportion of stars with planets. The detection of interstellar comets and asteroids ejected from other star systems shows that planetary system formation involves violent processes that scatter debris throughout interstellar space. This debris provides information about the prevalence and characteristics of planetary systems across the galaxy. Interstellar comets carry chemical signatures of their system of origin, potentially revealing details about star composition, planet formation processes, and the frequency of habitable environments around other stars. The chemical composition of Oumuamua's carbon dioxide ice may indicate formation in the outer regions of its original system, where temperatures allow carbon dioxide ice to remain stable over geological timescales. Such conditions may exist in debris disks of many star systems, suggesting that the raw materials for life could be widely distributed throughout the galaxy. If advanced civilizations do exist, they might use interstellar objects as natural camouflage for strategic scouting missions. This would be especially effective during periods when many natural comets appear simultaneously, providing cover for artificial visitors among genuine phenomena. The current autumn comet season creates exactly such conditions. From this perspective, the Fermi paradox may have a simple explanation. Alien visitors have been here but are clever enough to avoid detection while conducting their observations. Instead of announcing their presence through spectacular technological displays, they may prefer subtle reconnaissance to gather information without causing panic or defensive reactions from primitive civilizations like ours. The reconnaissance theory suggests that civilizations may be rare, but real, satisfying the Drake equation with low but non-zero values for factors such as the probability of life, developing technology, or the lifespan of technological civilizations. Even if only a tiny fraction of star systems develop, spacefaring cultures, the vast size and age of the galaxy could still produce interstellar scouting missions, occasionally. However, natural explanations for the unusual features of Oumuamua remain plausible, and perhaps more likely than an artificial origin. The volatile composition and rapid expansion of its coma, and the extreme polarization characteristics may all be the result of natural processes occurring in an object with a special formation, history, or unusual internal structure. The clear concentration of comets and asteroids in our sky in autumn 2025 may simply reflect improved detection capabilities combined with natural dynamical processes occasionally full of objects passing through the inner solar system at the same time. Our enhanced ability to detect and track faint objects causes previously invisible phenomena to suddenly become apparent. The scientific method requires that we consider all natural explanations before invoking extraordinary options. Occam's razor principle states that simpler explanations requiring fewer assumptions are usually more likely to be correct. Strange natural phenomena only require an extension of known physical laws, while artificial explanations require the existence of advanced extraterrestrial technology. However, this possibility cannot be completely ruled out if interstellar intelligence probes do exist. Their operational requirements would match many observable characteristics of Oumuamua, Long-duration missions would benefit from simple, robust systems capable of surviving thousands of years in interstellar space. Stealth requirements would favor designs mimicking natural phenomena while conducting scientific observations. Timing remains an issue for the interstellar reconnaissance hypothesis, as extraterrestrial reconnaissance missions would arrive precisely during humanity's brief, nascent technological phase. Our radio waves have been detectable for less than a century, and our space infrastructure only a few decades old. The coincidence of first contact occurring within such a narrow time window in human history seems remarkably convenient. A viable solution involves assuming that reconnaissance missions are frequent, rather than reactive to specific technological developments. If advanced civilizations regularly survey neighboring systems regardless of whether they contain obvious technological signatures, then the appearance of probes would follow statistical distribution laws unrelated to the development level of target civilizations. On the other hand, our technological signatures may be more detectable than we think. High-energy phenomena such as nuclear weapons tests, powerful radar systems, and satellite communications could be visible to advanced civilizations over much greater distances than those we usually consider. From this perspective, Oumuamua could represent a response to decades of increasingly obvious technological development. The search for extraterrestrial intelligence has focused mainly on radio signals and other electromagnetic radiation, but physical visitors may be much more common than remote communications. If civilizations prefer to gather information through direct reconnaissance rather than risk exposing themselves via long-range transmissions, we may have been looking for the wrong kind of evidence. Future observations of Oumuamua and other unusual interstellar objects will gradually answer these questions. If these objects turn out to be strange but explainable natural phenomena, with unusual but explicable characteristics, they will expand our understanding of planetary formation and evolution in other star systems. If they show evidence of artificial origin, they will revolutionize our understanding of life in the galaxy. The most profound implication of the Fermi paradox may be that advanced civilizations are present, but subtle, conducting observations through sophisticated methods, sufficient to avoid easy detection while gathering the information they need. The alien invasion or cosmic coincidence hypothesis continues as Comet Atlas relentlessly journeys towards the inner solar system. The scientific community finds itself engaged in a debate that a few years ago would have been considered absurd. Although the evidence is far from conclusive, it has accumulated to the extent that serious researchers are openly discussing possibilities far beyond conventional astronomical explanations. One side of this debate consists of astronomers with decades of research experience, comets and asteroids. Their explanations emphasize natural processes. The unusual brightness is the result of unique volatile components interacting with solar heat in ways our models have not yet fully grasped. The inverted tail shape reflects viewing angle effects combined with complex dust distribution patterns and extreme polarization characteristics, showing dust particle properties unlike those found in solar system objects, but still within the natural range of phenomena. These researchers only state the basic principle that extraordinary claims require extraordinary evidence. while the Atlas article shows unusual characteristics, none of which definitively exclude natural explanations. The abundant carbon dioxide, rapid coma expansion, and abnormal polarization could all result from an extraterrestrial origin. A comet in another star system where formation conditions and subsequent processing differ significantly compared to our local environment. On the other hand, a growing wave of opinion suggests that these accumulated anomalies represent more than mere statistical coincidence. Models of appearances in autumn 2025 include many bright comets and a wave of near-approaching asteroids, creating a coordination that seems unlikely to be the result of entirely random processes. The inverted tail shape, green luminescence, and rapid expansion combine to create a visual spectacle seemingly designed to attract attention. The conspiracy theory explanation emphasizes the timing and appearance of many unusual objects at the comet's star, all appearing within the same narrow time frame unless their appearances are somehow coordinated. The activity of asteroids in mid-September, combined with the unusual characteristics of the comet and striking visual features, create a natural narrative framework suggesting external arrangement. However, it is important to emphasize that the Atlas comet poses no direct threat to Earth regardless of its true nature. The closest approach of the comet to our planet will occur on 19/10/2025 at a distance of 1.8 astronomical units, equivalent to about 170,000 kilometers. That distance is farther than the distance from Earth to the Sun, making any direct impact scenario completely impossible. The comet's orbit will take it past many other planets on its journey through the inner solar system. It will pass quite close to Mars, Venus, and Jupiter, astronomically speaking, but these approaches are still millions of kilometers away. Even if the Atlas article were somehow artificially manipulated, its current orbit cannot threaten Earth or any other planet. The emotional appeal of strange explanations becomes understandable when faced with the visual spectacle presented by Atlas blue light. Geometric shapes, counterintuitive reflections, and rapid brightening create an appearance that science fiction has taught us to associate with alien technology or supernatural phenomena. Our cultural conditioning naturally leads to dramatic interpretations. When confronted with visually striking astronomical events, popular culture has prepared us to expect alien contact to involve dramatic announcements, obvious technological displays, or unmistakable signals leaving no doubt about their artificial origin. The reality can be much more subtle, involving precisely those missions designed specifically to avoid triggering defensive reactions from primitive civilizations like ours. From this perspective, the current debate may be exactly what advanced reconnaissance activities want to achieve, generating scientific interest and public discussion without providing conclusive evidence, thus avoiding immediate policy responses or social chaos. Ambiguity allows observation and research to continue, while avoiding possible panic if clear confirmation of alien visitation were made. The question of timing remains central to both explanations. Supporters of natural explanations argue that questions about timing remain central to both explanations. Proponents of natural explanations argue that improved detection capabilities and increased public interest in space phenomena create observational biases that make everyday events seem more significant than they actually are. We are simply better at finding and reporting unusual objects compared to previous decades. Proponents of strange interpretations counter that the clustering of events exceeds what statistical probability predicts, especially considering the rarity of interstellar visitors and the brief historical time frame. Systematic sky surveys are capable of detecting the coincidence of many unusual phenomena. Occurring during humanity's short technological adolescence seem to require an explanation. Beyond pure chance, professional astronomers working on the Atlas project usually maintain a neutral attitude with the public, while privately acknowledging that the characteristics of this object are pushing the limits of current understanding, especially polarization data showing measurements that do not match any natural object previously studied, requiring either significant extensions of current theory or consideration of more unusual hypotheses. The reaction of notable organizations is cautious, with major observatories and space agencies focusing on technical issues, characteristics that avoid speculation about meaning. This cautious approach reflects both scientific method and practical concerns about public reaction to more dramatic interpretations. However, the lack of new, high-resolution images from major space telescopes in September has fueled conspiracy theories, while operational constraints and conflicting schedules provide mundane explanations for the lack of data releases. Recently, this timing seems suspiciously convenient to those inclined towards more dramatic interpretations. The question of disclosure becomes particularly relevant. If the Atlas object represents something beyond natural phenomena, how will governments and scientific organizations handle the accurate confirmation of extraterrestrials? The social and economic impacts would be profound, potentially causing everything from religious crises to stock market crashes to fundamental changes in international relations. From this perspective, gradual disclosure through scientific debate may be a responsible approach to a potentially revolutionary discovery rather than shocking the public with dramatic announcements. The current process allows society to gradually adjust to possibilities that seemed impossible just months ago. As the Atlas continues to approach perihelion at the end of October, each new observation has the potential to shift the balance decisively towards natural or artificial explanations. The scientific community is watching with unprecedented attention. Whether an object from another star system or challenging our understanding of natural phenomena, or bringing humanity's first confirmed contact with alien technology, the importance cannot be overstated. We may be witnessing strange physical phenomena occurring on an unusual comet from another star system, or we may be witnessing the first confirmed evidence that we are not alone in the galaxy and that other civilizations possess the technology and interest necessary to study us from distances measured in light years. But, regardless of the true nature of the Atlas object, a troubling question has begun to arise among researchers tracking its progress. So, where are the detailed images we should see from our most powerful space telescopes? Where is Part 11? The images, where are they? The timeline of BA's observations of the Atlas shows a strange gap, causing both professional astronomers and conspiracy theorists to ask uncomfortable questions, while amateur observers worldwide continue to post impressive photos of the Blue Nebula 6 and the comet's unusual tail shape. Major space observatories that should provide the highest quality data remain mysteriously silent during the crucial September. The Hubble Space Telescope captured detailed images of the Atlas on 21/7, revealing a compact nucleus surrounded by its glowing dust shell. These observations provided important constraints on the object's size and established measurements, fundamental to its unusual characteristics, but as of 22/9, no further images from Hubble have been released to the public despite the comet continuing to brighten and appearing increasingly impressive. Similar to the James Webb Space Telescope, which conducted spectral observations on 6/8, revealing the composition of the carbon gel oil side of Comet SAO, and providing insights into its unusual chemistry. These breakthrough observations have shaken headlines worldwide and confirmed that Atlas is fundamentally different from previously studied SAO comets. However, despite the ongoing evolution of SAO comets and intense interest from the scientific community, no JWST images dated September appear in public databases. Gemini Observatory South has released a stunning high-resolution image that has captured the public's imagination and provided detailed views of the structure of the complex tail of Comet SAO. However, this spectacular photo was taken on 27/8 and released on Wednesday, September, meaning even this impressive image represents August data, rather than observations from September. Important under normal circumstances, this time gap would not be surprising. Large observatories operate under complex scheduling constraints with observing time allocated months or years in advance based on scientific priority and technical requirements. The upcoming conjunction, when Atlas passes behind the Sun from Earth's perspective, creates natural restrictions on opportunities to observe solar elongation, adding an extra layer of complexity. Most space-based telescopes cannot point too close to the Sun without risking damage to sensitive instruments as Atlas continues its journey inward, observing. It becomes increasingly difficult to do so safely, requiring careful scheduling and specialized procedures to protect expensive equipment. Exclusive time slots represent another common aspect of professional astronomy. Observing teams typically receive exclusive access to their data for predetermined periods, allowing them to conduct analysis and prepare publications before public release. This system protects scientific investment while ensuring quality control and peer review. Data processing procedures also cause delays between observation and public release. Raw telescope data needs calibration analysis and extensive verification before it can be meaningfully interpreted or safely released to the wider scientific community. Complex observations may take weeks or months to process properly. Excessive demand from major observatories creates additional constraints. Telescopes like Hubble and JWST receive far more observation requests than they can accommodate, forcing difficult choices about which targets deserve detailed study. Atlas competes with countless other scientifically important objects for limited telescope resources. However, despite these usual explanations, the timing of the observation gap is suspiciously convenient for those inclined to more skeptical interpretations. September is when Atlas began exhibiting its most remarkable and unusual behaviors, including rapid brightening, deviating from predicted light curves, and increasingly prominent green fluorescence. If government agencies or international scientific consortia had detected something truly extraordinary about Atlas, September would be exactly when they could impose information restrictions during confidential analyses. The gap in public data release might reflect deliberate concealment rather than routine operational constraints. Meanwhile, amateur astronomers worldwide have filled the information gap with their own observations. Dark skies in locations such as Namibia, Chile, and Australia have provided stunning images showing Atlas's changing appearance throughout September. While scientifically valuable, these images lack the spectral detail and calibration accuracy that professional observatories can provide. The contrast between rich amateur imagery and absent professional data creates an unusual information landscape. Social media platforms are flooded with impressive photos of Comet by Atlas with its blue coma and complex tail structure. While scientific databases often provide authoritative information, they are noticeably absent. The contributions of amateur astronomers have become particularly important in monitoring brightness, the evolution of the comet, and recording its changing appearance. A network of skilled amateur astronomers, proficient in using sophisticated equipment, has provided additional continuous monitoring, sometimes superior in timing compared to professional surveys. However, amateur observations cannot completely replace professional spectroscopy and high-resolution imaging, detailed chemical analysis, precise astronomical measurements, and calibrated photometry provided by space telescopes remain essential for understanding the true and unusual nature of Atlas. The absence of recent professional images becomes more significant when considered alongside the increasingly dramatic appearance of the comet observed in September, which should have recorded the onset of the unusual brightening phenomenon, the development of enhanced green fluorescence, and potential changes in the shape of the empty tail previously noted by observations. Instead, the public record shows a precise gap at the time. The most interesting scientific developments occurring at this time seem almost designed to maximize speculation about what might be happening behind closed doors at major observatories and international space agencies collaborating on astronomy. Usually ensure that important observations are widely shared within the scientific community, even if publication is delayed. The lack of any preliminary or final results from the September observations appearing on professional networks suggests that either those observations do not exist or access to them is more tightly controlled than usual. The upcoming convergence provides a natural explanation for the limited observation opportunities in October, but it does not explain the absence of data from September when observing conditions were still favorable. The comet remained well positioned for observation throughout most of September, with sufficient solar elongation for telescopes to operate safely in the future. The flyby of Mars on 3/10 is the final optimal opportunity for high-resolution observation before the conjunction makes observing Atlas difficult or impossible. From Earth-based platforms, many spacecraft currently orbiting Mars are planning observations. The opportunity during this close approach is likely to provide unique views of the comet's nucleus and coma structure. After the conjunction period in late October and early November, Atlas will gradually reappear in the pre-dawn sky, becoming observable again. For observers on Earth, this reappearance will offer new opportunities for observation, detailed features that evolved during the most recent close approach to the Sun. The open question is whether post-conjunction observations will fill the current information gap or the most important data was already collected during September when public access to professional observations suddenly ended. The scientific community awaits these observations with unprecedented interest, knowing they may finally resolve questions surrounding the true nature of Atlas. Part 12. Convergence point in the sky, a convenient blind spot. The cosmic dance occurring in 10-2025 creates what conspiracy theorists might call the perfect cover-up scenario. While astronomers see this as an unfortunate but predictable observational challenge, the superior conjunction period when Comet Atlas passes behind the Sun from Earth's viewpoint will render the comet invisible just as it reaches its peak activity. The convergence point occurs when an object's orbit takes it to the far side of the Sun as seen from Earth. In this alignment, the overwhelming brightness of the Sun prevents direct observation of the object, creating a temporary blind spot in monitoring our solar system. For Atlas, this critical observation gap will coincide almost perfectly with its closest approach to the Sun. The mathematics of celestial mechanics make this timing inevitable rather than suspicious. 21:10 marks both the new moon day and the moment Atlas reaches its minimum solar elongation, bringing it closest to the Sun's position. In the Earth's sky, the comet disappears in the dazzling sunlight invisible to ground-based telescopes and poses a danger to space observatories when observing directly. Operational teams regularly pause observations when targets approach the Sun's low elongation angles, risking sensitive equipment from scattered sunlight and thermal load, creating safety margins preventing observations closer than 15 to 30 degrees from the Sun's position. Depending on the specific telescope requirements and wavelength, these limits are neither arbitrary nor administrative regulations, but essential protection for billion-dollar equipment. Signal-to-noise ratios also degrade significantly when objects approach convergence with the Sun. Even if devices can safely point near the Sun, the excessive background brightness will overwhelm the relatively weak signals from Comet Atlas, making meaningful observation almost impossible. This is like trying to photograph a candle while looking directly at a spotlight. However, from a conspiracy perspective, this timing seems almost too convenient to be coincidental. If a government agency or an international scientific alliance wanted to block information about Comet Atlas at its most critical stage, they could not choose a better natural cover. The convergence on the comet neatly causes it to vanish from public view precisely when its unusual features should become most apparent. The period around perihelion, when the comet usually shows its most impressive activity, will mainly occur during the occultation. Comet Atlas will reach perihelion on 2910, developing maximum coma density and the most prominent comet tail, while still hidden from Earth observation until it reappears after convergence at the end of November. The peak activity period will end. However, the convergence does not cause a complete loss of information. Many spacecraft are positioned throughout the solar system, maintaining observation capability from different locations, unaffected by Earth's viewing restrictions. The Solar and Heliospheric Observatory SOHO regularly images the area around the Sun and can capture Comet Atlas during part of its convergence period. At this time, the Solar Terrestrial Relations Observatory, consisting of two spacecraft positioned ahead and behind Earth in its orbit, provide stereoscopic images of solar activity and the inner heliosphere. These platforms can observe Comet by Atlas from angles not disturbed by the Sun throughout the convergence period. The European Space Agency's solar orbiters tasked with studying the Sun from high latitudes and close distances can also provide unique observation opportunities. Its elliptical orbit takes it out of the ecliptic plane, offering viewpoints that might reveal by Atlas even during Earth's convergence. Some spacecraft orbiting Mars are planning opportunistic observations when by Atlas approaches the red planet on 310. High-resolution imaging science experiments on board the Mars Reconnaissance Orbiter, the color and stereo surface imaging system on the European EXO-Mars Trace Gas Orbiter, and the high-resolution stereo camera on Mars Express all have suitable capabilities for comet observations. These observations are a final chance for high-quality imaging before convergence renders Comet Atlas invisible from Earth. Data collected during the Mars flyby will provide important information about the nucleus structure, coma composition, and tail dynamics at a much closer distance than any Earth-based telescope can achieve. Professional astronomers and space agencies maintain active social media and share data according to protocols that usually ensure rapid dissemination of important observations. Observations from the Mars flyby, if they reveal anything unusual or confirm strange features, will appear in public databases and scientific announcements within days or weeks after collection. This timing coincides with increased solar activity approaching the solar maximum in its 11-year cycle. Coronal mass ejections. This timing coincides with enhanced solar activity as it approaches the solar maximum in its 11-year cycle, solar flares. Coronal mass ejections and intensified solar wind during this period can create spectacular interactions with comet tails, sometimes completely severing the ion tail or causing impressive brightness changes visible even to amateur observers. These natural interactions between the comet and the Sun can conceal or mimic artificial phenomena, creating additional ambiguity about the true nature of Atlas during this critical convergence phase. If the comet is equipped with an artificial system, the extreme solar conditions will provide natural cover for radiation steps. Unusual electromagnetic or time reappearance propulsion maneuvers become important to answer questions about the nature of Bi-Atlas. Astronomers predict the comet will appear from the convergence point at the end of November, becoming visible in the sky before dawn for observers in both hemispheres. Its brightness and appearance during this reappearance will provide important clues about how it evolved during its hidden period. At the convergence point, if the Atlas comet reappears with significant changes in brightness, tail structure, or other anomalies inconsistent with the natural evolution of the comet, that will reinforce arguments for strange explanations. Conversely, if it appears like a typical comet, after perihelion with predictable gradual brightness decrease and normal tail features, then the natural explanation will receive considerable support 19 out of 10 to when approaching Earth, although still at a safe distance. About 8 astronomical units will provide the best observation opportunity after convergence, allowing a few weeks for the comet to escape sunlight and become accessible again to large ground-based telescopes and in space once more. Amateur astronomy communities worldwide are preparing for the reappearance campaign organizing observation networks, and sharing data according to procedures to ensure comprehensive coverage when Atlas emerges from the sun's hiding place. Efforts from this base will provide important backup observations. If professional observatories encounter continuous data problems or operational restrictions, the convergence phase is not only an observational challenge, it acts as a natural test in information control and public transparency on how government agencies, scientific organizations, and international bodies handle information loss, providing insight into their decision-making and priorities regarding potentially sensitive astronomical discoveries if Atlas represents something beyond ordinary natural phenomena. The convergence period will offer a perfect opportunity for secret analysis. Without public scrutiny, advanced spacecraft with specialized sensors can conduct detailed studies during the lockdown period, with results kept confidential until policies are issued regarding information disclosure precedents. Such information control exists in military and intelligence circles, where sensitive observations are often kept secret for years or decades. The transition from scientific discovery to national security concern can easily occur if the Atlas comet has exhibited characteristics demanding government attention. From a more optimistic perspective, the convergence phase may simply be an unfortunate time preventing the public from observing one of the most important astronomical events in modern history. The comet's appearance at the end of November may herald a new era in understanding interstellar visitors and the nature of objects from other star systems. The convergence of Atlas creates perfect conditions for conspiracy theorists while simultaneously offering natural explanations, satisfying scientific skeptics. Like many aspects of interstellar visitor behavior, it maximizes ambiguity and controversy. But the convenient observational gap is not the only aspect of Atlas, seemingly borrowed from science fiction. The current situation bears an astonishing resemblance to a satirical film that warned precisely about this type of scenario where obvious threats are ignored or suppressed until it is too late to respond effectively. Part 13. Don't Look Up. The 2021 Netflix film Don't Look Up presented a dark comedy scenario where government officials, media, and corporate interests systematically suppress and distort information about an approaching comet threatening all life on Earth. Although the film was made as a satire on climate change denial and dysfunctional political situations by Atlas created unsettling similarities that many observers find hard to ignore in the film. Astronomers discovered a giant asteroid on a collision course with Earth but struggled to communicate. The urgency of the threat to a distracted public overwhelmed by celebrity gossip and political drama. Government officials manipulate information to gain political advantage, while tech billionaires propose solutions for profit, worsening the problem, and the media treating the impending apocalypse as entertainment content. The similarities with Bialas begin with that very discovery. Astronomers found an unusual object, with characteristics beyond common understanding, but their efforts to convey its importance were filtered through bureaucratic machinery of institutions, and media interpretations often distorted or downplayed the implications. The film's portrayal of government secrecy and information management resonates strongly with current observational distance regarding Bialas. In Download app, Officials know more about the comet's characteristics than they publicly disclose, conducting secret assessments while maintaining official positions that everything is under control. However, key differences distinguish the fictional scenario from our current reality. The comet in Don't Look Up poses a direct extinction threat to Earth, whereas by Atlas will pass safely. At a distance of 1.8 astronomical units on 19 to 10 plus 2, even the strangest interpretations of by Atlas's nature do not indicate any direct physical danger to our planet. The comet in the film was discovered only months before the impact, creating an atmosphere of immediate, urgent, and desperate crisis, whereas by Atlas has been tracked for over a year, with a precisely calculated orbit and its Earth flyby distance confirmed through multiple independent observations. It simply cannot collide or have a direct impact. However, the psychological dynamics depicted in Don't Look Up reflect many aspects of the current public reaction to by Atlas. Social media platforms are abuzz with competing theories, from natural explanations to bizarre speculations about alien espionage. The similar polarization between scientific authority and public skepticism that the film satirizes is unfolding in real time on digital platforms. The film's depiction of media sensationalism is mirrored in the coverage of by Atlas and the mid-September asteroid approaches. Headlines about near-miss asteroids and mysterious interstellar visitors generate clicks and engagement, while often obscuring the actual scientific content and safety assessments meant to inform the public. The film shows how legitimate scientific concerns are distorted when filtered through political and economic interests, prioritizing short-term gains over long-term consequences. Similarly, the by Atlas situation involves complex scientific questions interpreted through frameworks shaped by everything from government secrecy concerns to entertainment industry agendas about alien contact scenarios. One of Download App's most prophetic elements is its portrayal of extraordinary events becoming normalized through repetition, exposure, and media saturation. The fictional comet ultimately becomes just background noise competing for attention, with celebrity scandals and political controversies. Bialas faces similar risks of normalization, as initial excitement fades and convergence phases push it out of immediate view. The film's treatment of expert authority versus public skepticism seems particularly relevant to the current situation. In the film, astronomers struggle to maintain scientific credibility while competing with charismatic individuals who offer more emotionally satisfying narratives. The debate over by Atlas involves similar tensions between cautious scientific methods and more dramatic interpretations that capture the public imagination. However, the film's satirical framework should not be used to dismiss legitimate questions about transparency and information sharing related to by Atlas. The film was designed to highlight real issues, with the way organizations handle complex, long-term challenges not fitting neatly into existing political and economic frameworks. The recent absence of high-resolution images from space telescopes, combined with the favorable timing of the convergence event, creates natural information gaps that fuel speculation about deliberate concealment, while operational constraints offer mundane explanations. This pattern resembles information management, as depicted in the film Don't Look Up, where the film portrays public destiny and denial. also resonates with the current attitude towards astronomical phenomena. Many have become indifferent to reports of near-Earth asteroids, comet discoveries, and other space-related events, viewing them as mere entertainment rather than meaningful scientific observations that could reveal important information about our environment. Universe, don't look up. Ultimately suggested that humanity's greatest weakness does not lie in external threats but in our inability to process complex information and collective response to challenges that exceed the timeframes of normal political and economic cycles. The Atlas scenario examines similar vulnerabilities, although fortunately without mortal risks. As in the fictional script, the film ends with a comet impact event occurring despite full warnings and technological capability to prevent it, serving as a warning about the importance of maintaining institutional credibility and public trust, as well as scientific expertise. The Atlas scenario offers an opportunity to demonstrate that these systems can operate effectively when faced with truly unusual phenomena. The challenge for scientists, government officials, and media organizations lies in maintaining appropriate transparency, while avoiding both premature speculation and excessive secrecy. Don't Look Up illustrates how public trust can easily erode when institutions appear to prioritize political or economic considerations over honest communication about scientific uncertainties. As Atlas continues its journey towards convergence and eventual reappearance, the handling of information about its characteristics will be a practical test to see whether the missteps satirized in the film Don't Look Up are inherent human limitations or avoidable failures of leadership and communication. The film's strongest message is that extraordinary challenges require extraordinary cooperation and honest communication across institutional boundaries, whether dealing with climate change, responding to a pandemic, or the possibility of first contact with extraterrestrial intelligence. The risks are too great to play political games and manipulate information, as the film depicted. But while Don't Look Up focuses on political and social disorder in the face of imminent disaster, the Atlas scenario raises different questions about how humanity might respond to ambiguous but potentially revolutionary discoveries. The unusual characteristics of the comet do not threaten immediate destruction, but may signal changes in our understanding of life, intelligence, and humanity's place in the galaxy that could be as transformative as the speculations about the apocalypse in Part 14. The following scenarios are merely imaginative thought experiments designed to explore the outer limits of possibility, rather than predictions based on reliable evidence. While Atlas exhibits unusual features challenging current understanding, nothing in the observational data indicates an imminent threat to Earth or catastrophic outcomes, as it continues moving into the inner solar system. However, human imagination naturally gravitates towards dramatic possibilities when faced with phenomena that do not fit established models. Similar cognitive processes helped our ancestors survive by anticipating potential dangers, now creating worst-case scenarios about interstellar visitors exhibiting unexpected behavior. What would happen if the nucleus were significantly larger than current best estimates? The upper limit of the Hubble Space Telescope is about 2.8 km radius, combined with ground surveys, indicating a diameter of a few kilometers is the most reliable size limit currently available. However, these measurements depend on assumptions about surface reflectivity and geometric characteristics, which may not apply to objects with special components or unusual internal structures. A larger nucleus will contain a higher proportion of volatile materials, which may explain the rapid expansion of the comet's SAO ring and the unusual brightness evolution that has characterized the comet. Alas, throughout its approach, however, this scenario contradicts the most carefully calibrated observational data and would require systematic errors across many independent measurement techniques. What would happen if a fragmentation event occurred during the SAO Mars flyby, silently altering the dust amount and brightness of the SAO comet? SAO comets occasionally undergo cracking events when tidal forces or thermal stress exceed the structural integrity of their loosely bound nuclei. Such fragmentation often causes sudden increases in brightness and coma volume, as new surfaces rich in volatile materials are exposed to solar heat. A fragmentation near SAO Mars would be physically plausible, the gravitational pressures involved, and resulting changes in the appearance of Atlas would be detectable in light curve measurements and imaging data. However, precise orbit determination based on extensive astronomical observations would quickly reveal any significant changes to the orbit or physical characteristics of the object. But if that orbit undergoes subtle changes, undetectable by current orbital calculations, the precision of modern astronomy allows astronomers to predict the position of the Atlas comet many months in advance with kilometer-scale accuracy. This accuracy results from thousands of positional measurements taken over many months, producing extremely robust orbital solutions. To deceive or distort any significant orbital changes would require forces beyond gravitational forces from known bodies in the solar system, although outgassing from the comet nucleus can produce small accelerations. These non-gravitational forces usually follow predictable models related to solar heating and rotation cycles. Artificial propulsion systems would need to operate within very tight limits to avoid detection by current monitoring capabilities. What would happen if Atlas deployed small scout wind probes or tiny satellites disguised as natural meteoroids? This science fiction scenario would require technology capable of deploying payloads that survive atmospheric entry and operate on Earth's surface while maintaining communication with their mothership. Logistics for such operations would be challenging, requiring precise timing and advanced miniaturization technology. However, any objects launched from Atlas would follow predictable orbits, based on the comet's orbital mechanics and deployment circumstances. Worldwide meteor observation networks could detect unusual patterns in fireball activity if artificial objects enter Earth's atmosphere. In significant numbers, could the September asteroid encounters represent coordinated reconnaissance activity, rather than random coincidence in approaching the asteroid wave, including several objects that passed safely but stood out in Earth's vicinity, generating news and public attention. During the same period when Atlas was exhibiting its most unusual behavior, in fact, close asteroid approaches occur frequently throughout the year, with most encounters attracting minimal public attention, unless media circumstances generate unusual interest in September. The focus likely reflects improved detection capabilities combined with increased community awareness, as well as a real increase in asteroid activity. Solar maximum conditions in 2025 create additional possibilities for dramatic interactions between Bialis Atlas and the enhanced solar wind environment. Coronal mass ejections and increased particle radiation can trigger spectacular disconnection events. In the comet's tail, sometimes producing flares and unusual geometric configurations. Spectacular connections in comet tails sometimes produce flare-ups and unusual geometric configurations, which ordinary observers find unusual. These interactions between the Sun and comet represent normal phenomena, becoming more frequent and intense during periods of high solar activity. Despite their visual impact, such events follow well-understood physics and do not indicate threats beyond weather-related effects. In space, for which modern technology is designed to adapt, if something truly dangerous is detected, related to Atlas or any other object in the solar system. A warning chain has been established to quickly communicate threat assessments to authorities. Small planet centers coordinate global efforts to monitor potentially hazardous objects, while research centers, Near-Earth Object Laboratory of the Jet Propulsion Laboratory maintains continuous monitoring capability. The European Space Agency operates parallel systems, providing independent verification and cross-checking of orbital calculations and impact probability assessments. These international efforts ensure we have the most comprehensive view and real threats will be identified and communicated through official channels rather than hidden from public knowledge. The psychological appeal of doomsday scenarios often exceeds their objective probability, especially when dealing with phenomena challenging existing understanding or involving objects from outside our near-space neighborhood. Similar cognitive biases make conspiracy theories emotionally satisfying. Also, amplify perceived threats from unfamiliar sources. Anxiety is a normal response to genuine uncertainty, but the situation of Comet Atlas provides ample evidence, indicating the limited scope of realistic possibilities. The comet's orbit keeps it at a safe distance from all planets. Its physical characteristics remain within limits explainable by natural processes, and its behavior complies with laws consistent with strange but natural phenomena. The most effective scientific approach is to maintain appropriate caution while focusing on the great opportunity Comet Atlas offers to study a formed object around another star, whether it proves to be a natural phenomenon or something more special. This interstellar visitor carries information about cosmic processes and conditions, inaccessible to Earth astronomy by any other means. Data collected from Bialis will contribute to scientific understanding, regardless of which interpretation proves correct, if natural explanations prevail. The comet will expand our knowledge of planet formation and evolution in other star systems if stranger options are supported. Humanity will face profound challenges adapting to evidence showing intelligence and technology exist on a galactic scale. But even setting aside doomsday speculations and conspiracy theories, one aspect of Atlas's behavior continues to challenge scientific explanation and captures public imagination in ways beyond rational analysis. Part 15. Final Warning. The alien appearance of Atlas as it races toward its October rendezvous with the inner solar system. 3 basic features continue to distinguish this interstellar visitor from all other objects astronomers have ever studied, creating a combination of traits seemingly designed almost to attract attention and challenge scientific understanding. The first strange pillar remains the rapid brightening that deviated from the predicted light curve. In mid-September, the comet's brightness model represents some of the most reliable tools in astronomical prediction based on tens of thousands of careful observations and well-understood physics of how sublimating ice behaves under sunlight heating. When Atlas jumped above the expected trend line, it violated assumptions proven accurate. For countless previous comets, this unusual brightening was neither small nor ambiguous. The deviation was so clear that amateur observers worldwide noticed the comet appeared brighter than sky charts and prediction software. Professional astronomers found themselves recalculating models and wondering if they had missed fundamental aspects of how interstellar objects respond to solar heat. The second pillar relates to the extraordinary atmospheric expansion and chemical composition of the comet. The Comet atmosphere region, mainly carbon dioxide, extends hundreds of thousands of kilometers into space, demonstrating a scale of activity, challenging understanding about how a small nucleus can sustain such extensive gas and dust production. Spectral observations from the James Webb Space Telescope reveal a chemical ratio unlike anything in our local comet population. This chemical signature suggests that Comet Atlas formed under conditions significantly different from those that create comets in the solar system. With the high carbon dioxide content combined with a rapid expansion rate, indicating an unusual volatile composition or a more intense and efficient sublimation process. Current models predict for objects at distances from the comet to the Sun in the main belt, and perhaps most convincingly lie in the extreme polarization measurements that have challenged experts in finding explanations. Natural minimum polarization values of about 2.7% at a phase angle of around 70, with an inversion point near 17.7, representing features that no natural object has ever exhibited. Polarization measurements provide diagnostic capabilities that brightness and spectroscopy cannot match, revealing fundamental properties about how dust particles scatter light, based on their size, shape, composition, and surface texture. In fact, the dust of biolaws produces polarization signatures unlike any material previously studied, indicating formation under special conditions, or a composition of materials not found naturally in the solar system. This feature, unusual brightness, extraordinary gas expansion, and unprecedented polarization characteristics combined with a green luminescent spectacle and anti-tail geometry create an appearance that evokes thoughts of an artificial origin. The comet looks alien in ways that go beyond usual impressions and extend to precise physical measurements, challenging scientific explanations. Current orbital calculations confirm that Comet Atlas will maintain a safe distance from Earth throughout its passage through the solar system, with the closest approach on 19 to 10·2 at 1.8 astronomical units, ensuring that regardless of the comet's true nature, it poses no direct physical threat to our planet. The encounter with Mars on 3:10 represents a more valuable scientific opportunity, a scenario where a hazardous impact timeline observation leads to a conjunction creating a natural experiment on accessibility of information and scientific transparency. As of 22/9, no new high-resolution images from major space telescopes have appeared in public databases. Although the comet continues to evolve, and the scientific community is keen to record its unusual features. The spectacular photo from 27/8 by the James Mini South Telescope at the observatory remains the most detailed image taken by experts, highlighting the gap between amateur observations filling social media pages and the calibrated high-resolution data that major observatories usually provide during significant astronomical events. This absence is especially notable as the comet's appearance becomes increasingly impressive throughout September. The conjunction phase, beginning at the end of October, will render Atlas invisible from Earth-based platforms, just as it reaches peak activity near perihelion. This timing, although explainable through natural mechanics, creates perfect conditions for those inclined to believe in conspiracy theories, while posing real operational challenges for astronomers wanting to record the comet's behavior during its most active phase. However, spacecraft deployed throughout the system will maintain observational capability during signal loss due to conjunction. The Mars encounter on 3/10 may provide the last high-quality images before Atlas disappears behind the sun's glare, making these observations especially important to understand the comet's true characteristics. How the scientific community handles comet data will set important precedents for how humanity approaches astronomical discoveries, potentially revolutionary. The current combination of unusual observational features. Convenient information gaps. Potentially revolutionary. The current combination of unusual observational features, convenient information gaps, and dramatic visual appearances create conditions that challenge the credibility of institutions and public trust in scientific authority. Whether the Atlas case ultimately proves to represent a natural phenomenon or something extraordinary, its impact on astronomy and public perception has been significant. Comets have forced scientists to reconsider assumptions about objects between the stars, while demonstrating the rapid pace at which unusual observations can generate widespread speculation about extraterrestrial intelligence and reconnaissance missions. Honest assessments remain natural explanations, despite being stretched to fit BA. The unusual characteristics of Alaska have not yet completely ruled out volatile alien components. The unusual internal structure and formation conditions, unlike our solar system, can explain the observed anomalies without requiring an artificial origin. However, accumulating evidence challenges the comfortable assumptions about the shape of natural objects and how they should behave. Alas, operating near the boundaries of current scientific understanding, exhibiting features that require significant expansion of existing theories or consideration of alternatives, could fundamentally change humanity's perception of its place in the galaxy based on your request. I will revise the text to make the wording more fluent and suitable for Vietnamese listeners while also combining split sentences into complete sentences. The current state of knowledge shows an atlas representing the most unique natural object ever discovered from interstellar space, or the first confirmed evidence of the existence of advanced intelligence on a galactic scale, possessing the technology needed to carry out reconnaissance missions across light-year distances as the comet continues to approach perihelion. Each new observation has the potential to decisively answer these questions. The coming weeks will determine whether Alas BA will be included in textbooks as a strange phenomenon. But nature has expanded scientific understanding, or the object has confirmed that humanity is not alone in the universe. and that other civilizations are actively studying us from distances measured in light years. The closer it gets to the solar system, the stranger 3 Atlas looks. Does that appearance reflect a truly alien origin, or simply natural processes operating under conditions we have never encountered? That remains the most profound question in modern astronomy, as 3 Atlas appeared after the conjunction on at the end of November and December. Humanity will finally have the chance to find out whether the visitor coming later carried out the most sophisticated reconnaissance mission in the galaxy, or simply provided the most impressive display of strange natural phenomena in history. Observing the comet. The answer will reshape our understanding of physics and the prevalence of intelligence in the universe, making Comet Atlas one of the most important objects ever discovered in the Earth's sky.